So another 30,000 foot view video. What we're going to do in this video is take a key equation that we started Biochemistry 1 with and sort of map on all of the information that we know that's allowed us to understand how this equation proceeds. So here's that equation. We take fuel and we metabolize it, we combust it, we react it with oxygen, and we generate carbon dioxide, water, and energy. So importantly, we're going to map on all that we know about understanding what those fuels can be, highlighting that of the 4 biological molecules that we talked about, we're going to take nucleic acids off the table, not really a fuel molecule. And while carbohydrates, lipids, and proteins all can serve as fuels, carbohydrates and lipids are going to be our main fuels. I want you to think about the consumption of protein not as a fuel for energy, but as a way to obtain building blocks to either build new proteins in our body or to use those amino acids to generate amino acid derivatives that your body needs to do its biochemistry. But when we think about those fuels, really we're going to have a combination of different elements here. And I put them in this order in particular because when we have carbon and hydrogen, those are going to be our fatty acids. When we have carbon, hydrogen, and oxygen, those are going to be our carbohydrates. And then when we include nitrogen, that's going to be where we have proteins. And summarizing again what we know, the further we are along this oxidation continuum, the less of a caloric value we have. So fatty acids are worth 9 calories per gram, whereas carbohydrates and proteins are 4 calories per gram. And the reason that they're worth not as much is because we've kind of progressed down this oxidation continuum where there is more oxygen that's contained in these carbohydrates. So again, once you have oxygen built in as part of your molecular formula, you're just not worth as much as a fuel. So just putting down this little caveat here, I don't want us to think about proteins and amino acids that they're built from as a fuel. I want us to think about it as a source of building blocks. All right, so now that we've taken a little bit of a deep dive on those fuels that we have, let's remind ourselves and think again what it means when we metabolize or oxidize these fuels, right? When we think about oxidation, oxidation is really the loss of electrons. And I think I've mentioned this already in one of our 30,000 foot view videos, but we're going to keep this analogy going, imagining a sponge. And when we have a sponge, I want you to think about the sponge literally being the carbon atoms that we have there, and then water that can be in the sponge is going to be electrons. So fuel molecules basically have a lot of carbon atoms, and those carbon atoms and the other atoms that make up those fuel are held together by bonds that are electrons. Electrons are the energy. So when we oxidize and we lose electrons, I want you to think about squeezing the energy out of that fuel molecule as squeezing the water out of that sponge. Now, if we didn't have some way of collecting that water, we wouldn't be able to harvest that energy. So how we collect those electrons is we deliver them to middlemen. So we're going to have NAD plus and FAD. These are going to be our electron harvesters. We'll build on those a little bit more in this learning unit, but reminding you of information that you already know. These are the B vitamins that we've begun to study. Vitamin B3, niacin, is used to synthesize NAD. And then we've got vitamin B2, we've got riboflavin that's used to synthesize FAD. All right, so we take these are the oxidized form of these cofactors, and we're going to reduce them. So when they become reduced, when they gain electrons, they become NADH and FADH2. Again, our reduced cofactors now are high in energy because of their redox state, and they're going to go on to the electron transport chain. And once they're in the electron transport chain, we're going to learn about those details. Again, these electrons are delivered to the electron transport chain. They go through the electron transport chain, and through their transit through the electron transport chain, we are going to generate a proton gradient. So we're going to generate a proton gradient. And again, that's the intent of the electron transport chain, is to use that energy to pump protons and synthesize a proton gradient. Okay, and then that proton gradient is going to be used by ATP synthase. And that is going to be used to synthesize energy in the form of ATP. So to map on some pieces of things that we know, again, the electron transport chain and oxidative phosphorylation sort of taken together are going to be ETOP. Okay, so that gets us through sort of the water part of our sponge. We take the fuel, we squeeze out the electrons, they ultimately get used to pump a proton gradient, and that energy gets used to synthesize ATP. Well, we need to talk about what happens to the sponge part, what happens to those carbon atoms. So the carbon atoms that we have in our fuel, so carbon atoms, once they lose all of their electrons, they're fully oxidized. And so they're going to be converted into carbon dioxide. So again, fully oxidized carbon atoms are CO2. So again, if we think about a carbon atom, just as a little side note, a carbon atom in its fully reduced form, so fully reduced, is going to be carbon with 4 hydrogens. Fully oxidized is going to be carbon bound to 2 oxygens, carbon dioxide. So this is sort of the transit from, the most reduced form of carbon to the most oxidized form of carbon. So one other piece that we sort of haven't mapped on here is we did say that these electrons that are part of the electron transport chain are used to generate a proton gradient, but where do those electrons go once they are finished doing their proton gradient generation? So what we need to sort of map on here is that once those electrons finish their transit through the electron transport chain, they go to their final electron acceptor, which is molecular oxygen. We're going to force molecular oxygen to gain electrons, so become reduced. And when molecular oxygen becomes reduced, we generate water. So now we've sort of put all of these pieces together. We understand that the carbon atoms in the fuel are oxidized. We have molecular oxygen being reduced, and we can see now how we generate all of these pieces of this one equation. We started out Biochem 1 just looking at this little piece. One last piece that I want to sort of map on is, remember in our first 30,000 foot view video, we sort of talked about the 4 main metabolic processes that we're going to talk about that metabolize glucose. We've got glycolysis, pyruvate dehydrogenase chemistry, the citric acid cycle, and then electron transport and oxidative phosphorylation. So herein, we've talked about that 4th step. We've talked about electron transport and oxidative phosphorylation and how it feeds into this fuel equation. But I want to highlight where these other pieces sort of fit in here. And these other pieces fit in when we talk about sort of how we generate CO2 and how we fully, again, then oxidize those carbon atoms, and then how we sort of generate these reduced cofactors. So we'll learn a lot more later on, but I want to highlight, if we think about these 3 steps, we've got glycolysis, we've got pyruvate dehydrogenase chemistry, and then we've got the citric acid cycle. That was sort of steps 1, 2, and 3 of our carbohydrate metabolism. These are going to be places where we see the loss of electrons, the squeezing out of that water and generating reduced cofactors by delivering those electrons to NAD plus and FAD. But it also is going to be places where we generate CO2, particularly in pyruvate dehydrogenase chemistry and the citric acid cycle. We're going to generate a good bit of CO2. Okay, so that really sort of pulls all of this together with our understanding and mapping on of these metabolic processes to our key fuel metabolism equation.